Okay, good morning. Welcome to our new unit. This will be our first unit on term 4, and it is going to get split up a little bit. In order to prepare you best for your EOC, we need to cover certain elements from this unit, and then we need to cover another unit. And then what we'll do after the EOC is we're going to come back to this particular topic, exponentials and logarithms, to finish out the content in that. For those of you preparing to go into either pre-calculus or college algebra, you really need to have the whole unit, but the whole unit is not assessed on the EOC. So just a heads up. Another heads up, I am doing this exact same material in my college algebra class. And so for me, there's this weird overlap. And so please forgive me if I repeat myself a lot, or if you feel like I've left something out of an explanation. Please speak up and let me know, because it probably just means that I got my two classes flip-flopped in my head in what I covered in which class. So we're going to start this with just a real quick explanation of what an exponential graph is. So this year we've covered a lot of families of functions. So just as a quick review of families of functions, remember that families of functions are functions that have the same key traits. And then you learn what those key traits are, and then you graph them by doing transformations. So we have done families of lines. And we know that all lines pretty much look like this. And the key features of the line are the slope and the y-intercept. And once you know those key features, you can do pretty much everything you need to do with lines. We've done absolute value families, and that's actually the first family of functions that we introduce as a family. And those graphs look like V's. And usually the key features on that are what we call the transformations. So does it move right, left, up, down? Does it get wide? Does it get skinny? Those like vertical and horizontal compressions and stretches. Then we have quadratics. And we spend a lot of time in Algebra 2 discussing quadratics. Those are your parabolas. And those have probably more key features than I want to list here, but you've got your vertex, your axis of symmetry, the roots. We spend like a month on solving quadratic equations and how to find the x-intercept and the y-intercept of your quadratics. We also do parabolas in terms of transformations, like sliding them around the graph, the coordinate plane. Then we did higher order polynomials. And we didn't spend a lot of time. Now, polynomials, higher order polynomials, that's what we did starting in the third quarter. Lines and quadratics are polynomials. They're just like simple kinds of polynomials, degree 1 and degree 2. And then we spend some time looking at polynomials that are higher degree, and we look at their end behavior. And we look at the relationship between the factors and the roots, and we're able to sketch graphs of higher order polynomials based off of what we know about the end behavior and the number of roots. Then we did a square root. We did the square root family, and those look like this. They are the top half of a sideways parabola. And in that unit, we really layered in the concept of domain and range. And then we took a break of families of functions for a little bit, and we did operations on functions. So adding, subtracting, multiplying, dividing functions, finding inverse functions, and the relationship between the domain and range. And that pretty much summarizes all of Algebra 2 thus far. So what are we going to look at today? We are going to look at a new family called exponentials, and we're not going to go into a lot of detail about these graphs because they can be awkward to graph. And so what I want to do is just show you what the graphs look like so that you can see them. And if you see them, you'll recognize them, like that is the graph of an exponential. So here's the key with an exponential function. In an exponential function, the variable is in the exponent. Okay, that variable is in the exponent. That is your tip-off that you're looking at an exponential. So with a line, the exponent on the x is a 1. You can put it in the form y equals mx plus b. You know, to recognize a quadratic, you're looking for that x squared. Absolute value, you're obviously looking for the absolute value symbol, and you're looking for the x inside the absolute value symbol. For a square root, you're looking for the x underneath the square root. Well, for an exponential, you're looking for the x in the exponent. And then this right here that I have labeled as a b, b is a number greater than 0. Now you can, and b cannot be equal to 1. Because if it's equal to 1, 1 to like any power is just 1. And so you'd end up with a horizontal line. So you don't want b to be equal to 1. So that's your key feature, is that the variable is in the exponent. Now, what do they look like? Okay, that's kind of your parent function right there. There's two main ways that you can see your exponential graphs. One is like this, okay? And this is called exponential growth. And the idea is that it starts off very gradually. In fact, it might even look flat. It might look like a line with just a very, very low slope. And then it starts to curve. And once it starts to curve, we might even say it explodes. It starts getting steeper and steeper and steeper and steeper. But you might not see it for a long time. The other way it can look is kind of flipped around the other way. This would be a flip over the y-axis. So you could do this by putting a negative in the exponent. And this is called exponential decay because it's going the other way. So it starts off really, 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 really steep, and then it starts to level off. Okay, so that's pretty much what it looks like. If you see graphs that are shaped like that, I want you to recognize them as exponential growth and exponential decay. So one of the questions that I sometimes put on the quiz for this unit is just showing you a lot of graphs and saying, okay, match the graph with the family that it belongs to. And so you should be able to match lines and absolute values, parabolas. You should be able to match your square root. I didn't put the word root in there. Go fix that. Your square roots, you should be able to notice like a polynomial graph when you see it. And now we can add to that, you should be able to recognize an exponential. So examples of some exponential functions. We'll say exponential examples might be something like this. F of x is equal to 2 to the x power, or f of x is equal to 0.4 to the x power. This one where it's greater than 1 would be growth. This one where it is less than 1 would be decay. And your transformations also work the same way because, as we have said many, many times this year, math is consistent. So your transformations are the same as what they have always been. So, for example, well, what you really need to know for a new family is you need to know, okay, what's the inside, what's the outside, so that you know whether a graph is moving left, right, up or down, or flipping. So we'll take a look at a few examples. We'll do 2 to the x plus 3 minus 5. We'll do negative 2 to the x plus 4. We'll do 2 to the negative x minus 3. And then we'll do negative 2x minus 1 plus 2. Okay, so here's the deal. With your inside and outside, your left and right shifts and your up and down shifts. When we say inside, we mean inside the exponent. And outside, just like typically would be outside the entire function, often tacked onto the right-hand side, like added onto the end, but remember it doesn't have to be. So your up and down could be moved around to the front. So this one here would be left 3 and down 5, okay? Same transformations. Again, what you just need to know is, okay, where's my inside? Inside is your left, right, and outside is your up, down. So inside, we mean inside the the exponent. This one does not have anything inside the exponent, so there's no left or right. There is an up 4 though. And then as before, when you see a negative out in front, that is a flip over the x-axis. If you have a negative inside, so this is just like with the square roots, you have like a negative on the outside gives you a flip over the x-axis, and then a negative on the inside would give you a flip over the y-axis. So this one has a flip over the y, and it goes down 3 because the -3 is on the outside. And then here we've got one, it's got a flip over the x-axis. It goes right 1 and up 2. So flip over the x, right 1 and up 2. So everything that you've learned before with your transformations holds true. It's just, it can be actually really hard to see the transformations. You can see the flips pretty easily, but there's also some weird stuff with exponentials where you can have like your flips kind of replicate each other. So for example, making it look like making the number less than 1, or in other words, like kind of taking the reciprocal of the base, is the same thing as like flipping it over the y-axis, because you can play around with, so if you had like 2 to the x and then you had 0.5, well, 0.5 is really 1/2, and you know from now, like your laws of exponents, that is 2 to the -1, and there's your negative inside your exponent. So there's some like kind of weird things with like messing with the base and also introducing flips, and we don't really want to get into that. We don't want to muddy the water too much because it can get confusing. So we will have my air conditioner repairman come right now. Okay, so resuming our lesson. So that's everything that we're going to cover on exponential graphs, and we're going to move into a discussion on exponential equations. So I'm going to go ahead and put up on the screen a key idea for solving exponential equations. So here's the idea. If you have 3 to the x, so there's the exponential part of it. You've got the variable and the exponent. And that is equal to 3 squared. And I were to ask you, what does x equal? Okay, I think everybody would say x has to be equal to 2. And the way you'd reason that through is kind of flipping the reasoning around a little bit. You'd say, well, if x doesn't equal 2, then they can't be equal. So if x is 3, 3 to the third is not the same as 3 squared. If x is 1, 3 to the first is not equal to 3 squared. If x is even 2.1, since we have seen that exponents can be like fractions and decimals, that they wouldn't be the same. Now, that leads us to the principle that's going to allow us to solve equations this way. If b to the x is equal to b to the y, then x has to be equal to y. In other words, if the bases are the same, then we can set the exponents equal. So in this case, the exponents are x and y. So as long as I know that I have the same number as the base, then I can conclude that the exponents are equal. Try to avoid some improper ways that you might say it. So I don't want you to say that like the 3's in this example, that the 3's go away. They don't just go away. They don't disappear. Anytime something drops out in a math problem, there's always a reason for it. Canceling out is a little bit better in a sense, they do cancel out, but I would mostly just stick with we can set the exponents equal because the bases are equal. So as per usual, I'm going to work through an example. I'm going to give you some general steps to follow and then model them in the example. And then I'm going to work through 3 more examples, hopefully in 15 minutes, so that you can see the different ways that this works out. So starting off with our steps. So here are the steps, And here's the problem we are going to solve. 2 to the x power is equal to 8. So we're going to start with a nice simple one. The first step is to write both sides as powers of the same base. In other words, you want 2 to the something equals 2 to the something. Now, this might require you to do a little bit of scratch work, thinking. You might have to go grab your calculator and do some stuff with it. You might have to play around with it. So 2 to the first power is 2, 2 squared is 4, 2 to the third is 8, and we have a winner. So 2 to the third is equal to 8. So what I'm going to do is I'm going to keep the left-hand side the same, and I'm going to rewrite the 8 as 2 to the third. Second step is set the exponents equal. So in this case, my exponents are x and 3. So I'll go ahead and set x is equal to 3. And then my third step is to solve the resulting equation, which in this case is kind of silly because x is equal to 3 and there's nothing more you can do. So we've been able to solve it. So that's the general principle. Write both sides as powers of the same base. That's the step that is going to require you to think a little bit and to use your calculator to figure out what that number is. So what I'm going to do is work 3 more examples to show you some different variations on it. And I'm going to use an analogy. We'll try to address some of the common mistakes, and then we'll end class with a few practice. So here is our next one. It's 5 to the 5x is equal to 125 to the x plus 2. So I want you to notice a couple things about this. First of all, we made this one a little bit harder because we've messed around with the exponents. So we don't have nice, simple little exponents like just an x. We have 5x and we have x plus 2. Notice what's in the exponents here. I am going to use the Super Cool Exponent Club analogy to help you remember what to do. And as a general tip, something that you might do is try to write the bigger number as a power of the smaller number. So you try not to mess around with whatever the smaller base is. Try to stick to just the bigger one. But we are going to look at an example where you do have to mess with both of them. So step number 1. Write both sides as powers of the same base. So what I'm going to try to do here is write both sides with a base of 5. So that's going to require me to do a little bit of scratch work. 5 to the first power is 5. 5 squared is 25. 5 to the third power is 125, and I have a winner. You do not have to show that. Okay, that is me teaching and writing it down to explain where it's coming from. So I have 5 to the third power. You won't have to go that long to find it because the numbers get really big really fast. Okay, it goes back to that graph here. Once they start getting big, they're going to get really big really fast. And so you're not going to have to do generally like exponents of like 7, 8, 9, 10. The numbers are too big. So I'm going to take my 125 and I'm going to replace that with 5 to the third. Now, here comes like kind of the weird part. These guys were already in the exponent, the x plus 2. They are the Super Cool Exponent Club. In fact, they're downright snobby. And you know who those people are, okay? I hope we don't have them at Atlantic Coast, but we might. The Super Cool Kids, and they don't like it when you try to join their group. They're going to block off the lunch table. Like, they are just mean and snobby. And they belong to the Super Cool Exponent Club. They meet Tuesdays after school, and no one knows what they do, okay? So what they're going to do is they don't want the 3 here to join their club. And so they're going to put up their Super Cool Exponent walls. It's like sitting in the lunch table like, nope, no seats here. You can't come and join us. 3, we don't want you in our club. We were happy with just our club and we're not taking new members. Now, that might be like a silly analogy, but the point is to help you to remember to put parentheses around it. Because the x plus 2 is grouped together as the exponent's functioning as a grouping symbol. And so when you try to add something to the exponent, you need to remember that the x plus 2 was already grouped together. Step 2, set the exponents equal. So my exponents are 5x and 3 times x plus 2. And a lot of you will multiply, you'll distribute as you write that down, and that's totally fine. And then step 3, solve the resulting equation. So in this case, we actually do have an equation. So I'll go ahead and distribute the 3. So I get 3x plus 6, subtract 3x from both sides. So we get 2x is equal to 6, divide both sides by 2, and x is equal to 3. And there you go. Now we have solved our first exponential equation. I'll just kind of wait for a moment for those of you that need to write down some of those steps in your notebook so that I'm not zooming through the problems too quickly. The next problem, if you're ready to write it down, is 9 to the 2x minus 1 equals 3 to the 6x. And let's go ahead and I'll change the slides and I'll go ahead and write that down. So that's 9 to the 2x minus 1 equals 3 to the 6x. So step number 1, write each side as a power of the same base. So a general rule of thumb is to look at the bigger number and see if you can write the bigger number as a power of the smaller number. So we would start by doing like, okay, 3 to the first power is 3, 3 squared is 9, and there we have it. So I'm going to take out the 9 and replace the 9 with the 3 squared. But remember the super cool exponent club. There was already a 2x minus 1 in that exponent, and they're not accepting new members, okay? And you know what? In real life, let them do their own thing. They are not worth it. So go eat outside on a bench or something. It's nicer than the cafeteria table. Anyway, but for our purposes, math purposes, the point of the super cool exponent club is to remind you to put parentheses around it. Once you have the bases the same, okay, now we set the exponents equal. So we have 2 times 2x minus 1 is equal to 6x. And then our third step is solve the resulting equation. So I will distribute to get 4x minus 2 equals 6x. Subtract 4x from both sides. So I'll get negative 2 is equal to 2x. And divide both sides by 2 to get negative 1 is equal to x. And life is good. Negative 1 is equal to x. All right. And I'm just pausing for a moment to allow people a chance to write down the steps to the problem. And you should be writing down the steps of the problem. And you should be referencing them with the steps. I am trying to keep them color-coded so that the same colors are going with the steps so that you have this nice bank of problems to look at to see like the reasoning and how the reasoning aligns with the steps for solving the problem. Last example. 4 to the 2n minus 1 is equal to 32. Okay, now I've said to you as a general rule of thumb, take the smaller number and try to write it as a power, the bigger number and try to write it as a power of the smaller number. Now, you want to make sure that you're using your vocabulary right. So power of and multiple of are two different things. So let's just kind of take a look at this. We have 4 to the first power is 4. 4 squared is equal to 16. 4 to the third is equal to 64. And what you'll notice is that we don't hit the 32. It's true that 32 is 4 times 8. But that is a multiple because you're multiplying. It's not a power. And so I wanted to make sure that I had an example that addressed that. So not if, but when that happens, what you need to do is look at both sides and you're going to try to write both sides as a power of something smaller. Well, 4 is a pretty small number, so there's not a whole lot you can do with that. But you do know that 2 to the first power is 2. 2 squared is equal to 4. So you could write 4 as 2 squared. So now we have to go and see if we can write 32 as a power of 2. So 2 to the third is 8. And you would do this on your calculator, okay? 2 to the fourth is 16. And you just kind of make some notes off to the side. And we have it, okay? We can take both the 4 and the 32 and write them as powers of 2. Just grab your calculator and start doing them out. If you do not know how to use the exponent button on your calculator, because I do not want you doing 2 times 2 times 2 times 2 times 2 on your calculator. It's a recipe for losing track of how many 2's you have in there, and it's going to take you forever. There's a button on your calculator that will do the exponents for you. Make sure you know how to use it. Okay, so on the left-hand side here, I'm going to take out the 4 and replace it with 2 squared. Now remember, we have the super cool exponent club going on. They are just nasty people across the board. All right, they are not letting the 2 come in. And then the 32 is 2 to the 5th. Once you have it as powers of the same base, now you can go ahead and set your exponents equal. Now I mentioned a lot of you can distribute as you're writing it down. So instead of copying down 2 times 2n minus 1, you'll actually do 4n minus 2, and that's totally fine. And then step 3 is solve. So 2 times 2 is 4, 2 times 1 is 2. We're going to add 2 to both sides, so we get 4n is equal to 7. Divide both sides by 4, and n is equal to 7/4, and everybody thinks they did something wrong because it's a fraction. But fractions are numbers, so there you go. All right, so I'll wait again for a moment or two for those of you that are writing it down to be able to write down everything. Remember that if you're in a face-to-face class, that these notes will be posted on Teams, and the video itself is posted on YouTube, so you can come and find it and rewatch it again as needed. Now, there are 2 practice problems that go along with this lesson, so I'm going to go ahead and put both practice problems up on the screen, and then I will very quickly, in the last 3 minutes of the video time, put the solutions in the video for those of you that need to see it because you're watching it on your own. Okay, here are the 2 practice problems. 8 to the 4x plus 2 equals 64. There's actually 2 ways that you can do that using 2 different bases. See if you can find the easier way to do it. And the second one is 81 to the a plus 2 equals 3 to the 3a plus 1. I'll hold here for a few moments so people can copy that down, and then I will work the problems out in the remaining 3 minutes of the video. Okay, here's the first one. I actually did it 2 different ways. The easier way to do it is to recognize that 64 is a power of 8. It's 8 squared. And so you would change that to 8 squared. Setting the exponents equal, you'd have 4x plus 2 equals 2. Subtract 2 from both sides. You get 4x equals 0. Everybody panics because 0, but 0 is awesome. Divide both sides by 4. 0 divided by 4 is 0. That's not a problem, okay? You can take nothing and say, I'm going to divide my nothing into groups, like every group has nothing. Okay, what you can't do is take something and put it into nothing. So it does matter where the 0 is. One way is okay, the other way isn't. Now, some of you might have tried to put both sides as a power of 2, and that would also work. So 8 is 2 to the 3rd power, and in this case, you'd have to remember your super cool exponent club. 64 is 2 to the 6th. Set the 2 exponents equal. Distribute through, so you get 12x plus 6 is equal to 6. Subtract 6, and now you're back to the 0. Divide both sides by 12, and 0 divided by 12 is 0, just like 0 divided by 4 is 0. So either way, you should get 0 as your answer. The other problem, you need to take the 81 and write it as a power of 3. So off here to the over here to the right, I have my scratch work until I get 3 to the 4th power equals 81. Now, there's only so many numbers that you can use here without the numbers getting super huge. So the more you do these problems, you will begin to recognize certain powers of numbers. So you take out the 81, replace it with 3 to the 4th. Then remember your super cool exponent club. They don't want the 4 to join. Then you set the 2 exponents equal. Distributing through on the left, I get 4a plus 8 equals 3a minus 1. Subtract 3a from both sides, so you have 1a plus 8 equals 1. Subtract 8, and you get a is equal to 7. So those are the solutions to the other 2 problems. If you're watching this on your own, you can pause the video, take a look at the solutions longer, or rework it, or make that work for you however you are doing it at home. And that concludes our first lesson on exponential equations.